In May 1964, two radio astronomers Arno Penzias and Robert Wilson were having a problem. They worked for Bell Labs in Holmdel, New Jersey. Their job was to use a massive 20-foot horn-shaped antenna to study radio signals from the Milky Way. This antenna was originally built for Project Echo, an early satellite communication experiment. By 1964, it was obsolete for that purpose, but it was one of the most sensitive radio receivers on the planet. Perfect for astronomy, except for one thing, a noise. There was a persistent, annoying hiss in their data. It came from every direction they pointed the antenna. It was there day and night, all year round. The signal was weak, corresponding to a temperature of about 3.5 degrees Kelvin, just a little above absolute zero. But it was everywhere and it wouldn't go away. They spent a year trying to eliminate it. They thought it must be an equipment malfunction. They checked the amplifiers, they rewired the connections. They pointed the antenna at New York City to see if it was urban interference. The hiss remained. Their most famous attempt involved a pair of pigeons that had been nesting in the throat of the giant antenna. They figured the birds and what they left behind might be the source of the noise. They captured the pigeons and cleaned the antenna, removing what Penzias later described as a white dielectric material. The hiss was still there. The pigeons, released a few miles away, promptly flew back and re-nested. The astronomers had to take more permanent measures to remove the birds. Even with the pigeons gone for good and the antenna thoroughly cleaned again, the noise persisted. They were stuck. The noise was real. It wasn't from their equipment. It wasn't from the city. It wasn't from our solar system or even our galaxy. It was coming from everywhere in the universe. At the same time, just 30 miles away at Princeton University, a team of physicists led by Robert Dicke was building their own radio antenna. You know, they weren't just building it for fun. They were specifically looking for a faint microwave signal spread across the entire sky. They had a theory. If the universe began in a hot, dense state of Big Bang, then the light from that initial fireball should still exist. It would be incredibly stretched out and cooled by billions of years of cosmic expansion, but it should still be detectable as a faint microwave glow. A friend told Penzias about Dickey's work. Penzias called him. On the phone, Penzias described the persistent, unexplained noise he and Wilson had found. As the Princeton team listened on speakerphone, the reality sunk in. Dicke famously turned to his colleagues and said, "Boys, we've been scooped." Penzias and Wilson had stumbled upon the afterglow of creation. In 1965, two papers were published side by side in the Astrophysical Journal. One by Penzias and Wilson described their measurement of an excess antenna temperature. The other, by Dicke's team, explained its cosmological importance. This discovery, the cosmic microwave background radiation, became the single most powerful piece of evidence for the Big Bang. Penzias and Wilson won the Nobel Prize in Physics in 1978 for finding a noise they had tried their best to get rid of. Number 20, the arrow of time points backwards. The universe has never been observed to run in reverse. An egg can fall and break, but a broken egg will not spontaneously reassemble itself and leap back into your hand. A star burns its fuel and dies, but a cloud of cold gas and dust does not suddenly coalesce into a dead star and then unburn itself. This one-way street for events is what we call the arrow of time. It is driven by a fundamental principle of physics called the second law of thermodynamics. This law states that the total entropy or disorder of a closed system can only increase over time. A clean room can get messy. A messy room does not spontaneously become clean. There are vastly more ways for things to be disordered than for them to be ordered. The universe as a whole is a closed system. The fact that the universe today is not a uniform, featureless, high-entropy soup of particles means it has not had an infinite amount of time to reach that state. If the universe had existed forever in a static state, it would have reached maximum entropy an infinite time ago. Everything would be the same temperature. There would be no stars, no galaxies, no life. Just a thin, cold, boring equilibrium. This is sometimes called the heat death of the universe. The fact that we are here in a universe full of structure and activity is evidence that this state has not yet been reached. And this points directly to a beginning. For entropy to be increasing now, it must have been lower in the past. And if you go back far enough, it must have been at its lowest possible point. The Big Bang model provides exactly this. It proposes a universe that started in an incredibly low entropy state. An intensely hot, dense, and remarkably uniform condition. This highly ordered initial state is the ultimate clean room. Since that moment, the universe has been expanding, cooling, and getting more disordered. Stars form, burn out, and scatter their elements, galaxies collide, black holes evaporate over immense timescales. Every physical process contributes to this overall increase in entropy. The forward march of time itself is a consequence of the universe starting in a highly ordered state and moving towards a more disordered one. An eternal, unchanging universe has no explanation for the arrow of time. The Big Bang is the only model where the initial conditions make sense of the fact that time moves forward and not backward. The universe had a beginning, and the one-way flow of time is the perpetual echo of that starting point. Number 19, distant galaxies are warped by gravity we can't see. In 1979, astronomers Dennis Walsh, Bob Carswell, and Ray Wayman observed a strange object in the sky. It was cataloged as QSO 957 plus 561 AB. It looked like two quasars, incredibly bright and distant galactic cores sitting right next to each other. They were almost identical. They had the same redshift, meaning they were at the same distance from us, about 9 billion light years away. They had the same light spectrum. It was too much of a coincidence. It wasn't two quasars. It was one quasar appearing twice. This was the first confirmed discovery of a gravitational lens. Between us and the quasar, there was a massive galaxy about 4 billion light years away. This galaxy was invisible in the initial observations, but its immense gravity was bending the fabric of space-time around it. Albert Einstein's theory of general relativity, published in 1915, predicted this. The theory says that mass does not create a force of gravity, but rather it curves space-time itself. Objects then follow these curves. Light is no exception. When light from a distant object passes by a very massive object, like a galaxy or a cluster of galaxies, its path is bent. The massive object acts like a lens. It can magnify, distort, or even create multiple images of the background object. We see this effect everywhere we look in the deep universe. Sometimes we see 4 images of a single quasar arranged in a cross shape, called an Einstein cross. Sometimes, if the alignment is perfect, the light from a distant galaxy is smeared into a perfect circle, called an Einstein ring. More often we see faint blue, distorted arcs of light, which are the stretched-out images of background galaxies whose light has passed through a massive galaxy cluster. This phenomenon of gravitational lensing is a powerful piece of evidence for the Big Bang model. First, it confirms general relativity over cosmological distances. The Big Bang model is built entirely on the foundation of general relativity. If Einstein's theory were wrong on these large scales, the entire Big Bang framework would collapse. Gravitational lensing proves that it holds up. Second, lensing allows us to map the distribution of mass in the universe, including mass we cannot see. The amount of lensing we observe in galaxy clusters is far greater than what could be produced by the visible stars and gas alone. This is one of the strongest pieces of evidence for the existence of dark matter, a mysterious substance that makes up about 85% of the matter in the universe. The Big Bang model predicts the existence of dark matter and requires it to explain how galaxies formed. And lensing lets us see where this dark matter is, and the amount we find matches what the model needs. It shows us that the universe is structured in the way the Big Bang predicts, with vast filaments of dark matter forming a cosmic web on which galaxies are built. Number 18, the first galaxies look different. When we look at very distant objects in the universe, we are also looking back in time. As light travels at a finite speed, about 300,000 kilometers per second, it takes time for light to reach us. The light from the sun takes 8 minutes to get here. The light from the nearest star, Proxima Centauri, takes over 4 years. The light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years. So when we look at Andromeda, we see it as it was 2.5 million years ago. Using powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope, we can look at galaxies so far away that their light has been traveling for over 13 billion years. We are seeing the universe as it was when it was just a few 100 million years old. If the universe were eternal and unchanging, as the old steady-state theory proposed, then galaxies everywhere should look roughly the same. An old galaxy nearby should look similar to an old galaxy far away. A young galaxy nearby should look similar to a young galaxy far away. The universe should be homogeneous in time as well as in space, but this is not what we see. When we look back in time at the earliest galaxies, they are different. They are generally smaller, more irregular, and bluer than the galaxies we see today. The blueness comes from a high rate of star formation. These early galaxies are vigorously churning out massive, hot, blue stars. These stars live fast and die young, so we only see them in galaxies that are actively forming stars. Modern galaxies, like our own Milky Way, are much larger and more settled. They have well-defined structures like spiral arms and central bulges. They have a mix of old red stars and some younger blue stars. The rate of star formation is much lower. We also see evidence of mergers. These small early galaxies are constantly crashing into and combining with each other. Over billions of years, these mergers build up the large mature galaxies we see in the nearby universe. This observation of galaxy evolution is a direct confirmation of the Big Bang model. The model describes a universe that starts hot and dense and then expands and cools. In this scenario, matter slowly clumps together under gravity. Small clumps form first, which then merge to form larger and larger structures. Small, irregular protogalaxies should form first and then evolve over cosmic time into the grand spiral and elliptical galaxies of today. So, the fact that the universe's galactic population has changed over time is a clear sign that the universe itself has a history. It had a beginning, and it has been evolving ever since. Number 17, quasars only exist in the distant past. Quasars are some of the most luminous objects in the universe. A single quasar can be hundreds of times brighter than our entire Milky Way galaxy. The word quasar is short for quasi-stellar radio source because when they were first discovered in the 1950s and 60s, they looked like single points of light, like stars, but were emitting powerful radio waves. We now know that a quasar is not a star at all. It is the intensely bright core of a very distant young galaxy. At the center of this galaxy is a supermassive black hole, millions or even billions of times the mass of our sun. As gas, dust, and even whole stars fall into this black hole, they form a swirling, superheated disk of material called an accretion disk. The friction and gravitational forces in this disk heat the material to millions of degrees, causing it to glow with incredible intensity across the entire electromagnetic spectrum. Here is the crucial point. When we look at the nearby universe, we do not see quasars. Here they are gone, but when we look deep into space, and therefore far back in time, we see them in great numbers. The peak of the quasar era was about 10 to 12 billion years ago. In this period of the universe's history, they were common. As we look at more recent epochs, their numbers drop off dramatically. This observation is a major problem for any theory that suggests the universe is eternal and unchanging. If the universe was the same yesterday as it is today, quasars should be randomly distributed throughout space and time. We should find as many nearby as we do far away. We do not. The Big Bang model provides a perfect explanation for this. In the early universe, galaxies were just forming. They were rich in gas, the fuel for supermassive black holes. As galaxies merged and interacted frequently in the crowded early cosmos, this gas was funneled towards the central black holes, switching on the quasars. The universe was a much more violent and chaotic place. Over billions of years, this fuel supply was used up. The gas in galaxies settled into stable orbits in stars and disks. The frequent mergers became less common as the universe expanded, and galaxies grew farther apart. The supermassive black holes at the centers of most galaxies, including our own Milky Way, became quiet and dormant. The quasar era ended. The fact that quasars only exist at a specific time in the universe's past is powerful evidence that the universe has evolved over time from a different state. It is not static, it had a dynamic youth, and has since settled into a more sedate middle age. Number 16, the universe is surprisingly flat. The shape or geometry of the universe on the largest scales can be one of three things. It can be closed, like the surface of a sphere. In a closed universe, if you traveled in a straight line for long enough, you would end up back where you started. A closed universe has positive curvature. It can be open, like the surface of a saddle. In an open universe, parallel lines would eventually diverge. An open universe has negative curvature. Or it can be flat, like a sheet of paper. In a flat universe, parallel lines stay parallel forever. This is the familiar Euclidean geometry we learn in school. A flat universe has zero curvature. The geometry of the universe is determined by its total density of matter and energy. If the density is above a certain critical value, the universe is closed. If it is below that value, it is open. If it is exactly at that critical value, the universe is flat. For decades, astronomers tried to measure this geometry. The measurements were incredibly difficult, but with the advent of precise observations of the cosmic microwave background CMB by satellites like WMAP and Planck, we got an answer. The universe is flat. To an astonishingly high degree of precision, our measurements show that the density of the universe is within 1% of the critical density needed to make it flat. This is a very strange result. The Big Bang model, in its original form, does not predict this. In fact, a flat universe is a very unstable state. If the early universe had been just a tiny fraction off from being perfectly flat, that deviation would have been magnified enormously over 13.8 billion years of expansion. For the universe to be so close to flat today, the density of the very early universe must have been tuned to the critical density to an accuracy of 1 part in 10 to the power of 60. That is like measuring the distance to the nearest star and being accurate to within the width of a human hair. This flatness problem was a major puzzle. Why is the universe so finely tuned? The solution came in the form of a theory called cosmic inflation, developed in the early 1980s by physicists Alan Guth and Andre Linde. Inflation proposes that in the very first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated exponential expansion. It grew from a size smaller than a proton to the size of a grapefruit in an unimaginably short time. This incredible stretching process would have flattened any initial curvature the universe might have had. Think of the surface of a tiny, crumpled balloon. If you suddenly inflate that balloon to the size of the Earth, the small patch you are standing on would look almost perfectly flat. Inflation takes any initial geometry and stretches it so much that our observable universe today appears flat. So, the observed flatness of the universe, while a problem for the simple Big Bang model, becomes a powerful piece of evidence for the inflationary Big Bang model, which is our modern understanding of the universe's first moments. Number 15, the universe is smooth on the largest scales. If you look at the universe on a small scale, say the size of our solar system or even our galaxy, it is very lumpy. There are planets, stars, and galaxies separated by vast regions of mostly empty space. But as you zoom out and look at the universe on the largest possible scales, a different picture emerges. On scales of hundreds of millions of light years, the universe starts to look remarkably uniform. The distribution of galaxies and galaxy clusters becomes smooth and even. There is no special place in the universe. It doesn't have a center or an edge, and it looks the same in every direction. This idea that the universe is the same everywhere and in every direction on large scales is called the cosmological principle. It is a fundamental assumption of the Big Bang model. This is a very specific and testable prediction. If the universe was not the same everywhere, we would expect to see huge variations in the distribution of galaxies. For example, there might be a massive concentration of galaxies in one direction and very few in another. We do not see this. Large-scale galaxy surveys like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, and they confirm this large-scale smoothness. The most powerful evidence for this uniformity, however, comes from the cosmic microwave background CMB. The CMB is light from the very early universe, and it bathes the entire sky. This light is incredibly uniform in temperature. It is 2.725 Kelvin no matter which direction we look. The variations in temperature are tiny, on the order of 1 part in 100,000. This tells us that the universe, when it was only 380,000 years old, was incredibly smooth and homogeneous. This smoothness presents a puzzle known as the horizon problem. How could two regions of the universe, now on opposite sides of the sky, have the exact same temperature? In the standard Big Bang model, these regions were never in causal contact. They were too far apart for light or any other information to have traveled between them to even out the temperature. It is like finding two people on opposite sides of the Earth who have never met or communicated, yet have somehow managed to write the exact same book, word for word. The solution, again, is cosmic inflation. During that initial burst of exponential growth, a tiny subatomic region of space that was in thermal equilibrium, the same temperature, was stretched to a size larger than our entire observable universe. All the regions we see in the CMB today were once in close contact before inflation blew them apart. Inflation explains how the universe could have become so smooth and uniform on large scales. The observed homogeneity of the universe is therefore strong support for the inflationary Big Bang model. Number 14, we cannot find any magnetic monopoles. In the world of magnetism, there is a fundamental rule: you can't have a North Pole without a South Pole. If you take a bar magnet and cut it in half, you do not get a separate North Pole and a separate South Pole. You get two new, smaller bar magnets, each with its own North and South Pole. You can keep cutting the magnet down to the level of a single atom, and you will still find a dipole, a north and a south. A magnetic monopole, a hypothetical particle that is just a north pole or just a south pole by itself, has never been. This is strange because our best theories of particle physics, known as grand unified theories guts, predict that they should exist. These theories attempt to unify 3 of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, and the electromagnetic force, into a single force at the incredibly high energies and temperatures of the early universe. According to these theories, as the universe cooled just after the Big Bang, a phase transition should have occurred, similar to water freezing into ice. This transition would have created defects, and these defects would be magnetic monopoles. The theories predict that they should have been created in huge numbers. They would be very massive and stable. So where are they? The universe should be full of them, but extensive searches have turned up nothing. This is the monopole problem. The absence of magnetic monopoles was a major challenge to both cosmology and particle physics. Once again, the theory of cosmic inflation provides a neat solution. Inflation happened in the first tiny fraction of a second, after the GUT phase transition that would have created the monopoles. The period of extreme rapid expansion would have taken any monopoles that were created and spread them out so thinly across the universe that the chance of finding one in our observable patch of the cosmos is practically zero. It is as if you took a single grain of sand and scattered it throughout a volume of space the size of the solar system. Or the grain of sand is still there, but you would be incredibly unlikely to ever find it. So the fact that we do not see any magnetic monopoles, which should have been created in abundance according to our best particle physics theories, is not a failure of the Big Bang. Instead, it is a powerful piece of circumstantial evidence for cosmic inflation, which is a crucial part of the modern Big Bang model. It explains an absence. It explains why we do not see something that we otherwise should. Number 13, the oldest light is slightly lopsided. The cosmic microwave background CMB is the oldest light in the universe. It is a snapshot of the cosmos when it was just 380,000 years old. On the whole, this light is incredibly uniform in temperature, but it is not perfectly uniform. There are tiny fluctuations, hot and cold spots, that are only about 1 part in 100,000 different from the average. These tiny variations are crucial. They are the seeds that grew into all the structures we see today, like galaxies and galaxy clusters. But there is another property of this light besides its temperature, its polarization. And light is an electromagnetic wave. It has an electric field and a magnetic field that oscillate. Polarization refers to the orientation of the electric field's oscillation. Most light sources, like the sun or a light bulb, are unpolarized. The light waves oscillate in all directions randomly, but light can become polarized if it scatters off of something. For example, light scattering in the atmosphere makes the blue sky polarized, which is why polarized sunglasses can reduce glare. In the early universe, just before the CMB was released, the universe was a dense, hot plasma of protons and electrons. Light photons was constantly scattering off of the free electrons. This scattering process polarized the light. The Big Bang model, particularly with the inclusion of inflation, makes very specific predictions about the patterns of polarization we should see in the CMB. There are 2 main types of polarization patterns known as E modes and B modes. E modes are a type of pattern that can be created by the simple scattering of light in the plasma. They have been detected and mapped in detail, and they match the predictions of the standard cosmological model perfectly. They give us information about the motion of the plasma in the early universe. B modes are a different, swirling, or curly pattern of polarization. They are much harder to create. The most significant source of B modes is thought to be gravitational waves rippling through space-time in the first moments of the universe during the period of inflation. Detecting these primordial B modes would be direct evidence of inflation and would give us a glimpse into the physics of the universe at unbelievably high energies. While a definitive detection of primordial B modes is still elusive and a major goal of modern cosmology, the detection and mapping of the E mode polarization is already a major triumph. The patterns we see are exactly what the model predicts. They confirm our understanding of the conditions in the early universe and provide yet another layer of evidence that the Big Bang picture is correct. Number 12, sound waves, left ripples in the fabric of space. In the first 380,000 years of the universe, it was a very different place. It was not transparent. It was an opaque, hot, dense soup of protons, electrons, and photons, light particles, all interacting with each other. This soup was not perfectly uniform. There were tiny density fluctuations likely created during inflation. Some regions were slightly denser than others. The immense gravity of these denser regions pulled matter in. But the photons trapped in the soup exerted an outward pressure, this cosmic tug of war between gravity pulling in and radiation pressure pushing out created ripples or waves that traveled through the primordial plasma. These were, in effect, sound waves. They were not sound we could hear, but they were pressure waves moving through the cosmic fluid at more than half the speed of light. These sound waves traveled outward from every point of overdensity. Then, at 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event is called recombination. Suddenly, the photons were free. They were no longer scattering off of electrons and could travel freely through space. This is the light we see today as the cosmic microwave background. At the moment of recombination, the sound waves were frozen in place. The wave had traveled a specific distance from its starting point. This distance is known as the sound horizon. So at recombination, the universe was left with a very specific pattern imprinted upon it. Every initial overdensity was surrounded by a shell of slightly higher density at a radius equal to the sound horizon, which was about 480,000 light-years across at that time. This pattern did not disappear. As the universe expanded, this characteristic scale expanded with it. Today, that distance corresponds to about 500 million light-years. This means that if you pick any galaxy, you are slightly more likely to find another galaxy 500 million light-years away than you are at 450 or 550 million light-years away. This preferred distance acts like a standard ruler imprinted on the cosmos. Astronomers searched for this signal for years. In 2005, two independent teams using data from the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey announced they had found it. They had measured the distribution of millions of galaxies and found this subtle but clear statistical preference for a separation of 500 million light-years. This phenomenon is called Baryon Acoustic Oscillations, BAO. The detection of the BAO signal was a landmark confirmation of the Big Bang model. It matched the size predicted from CMB observations perfectly, linking the physics of the very early universe to the structure of the universe today. It is like finding a fossilized sound wave from the dawn of time. Number 11, there is a faint glow of ghostly particles. In addition to photons, the Big Bang should have produced a huge number of other particles. One of the most abundant of these should be neutrinos. Neutrinos are incredibly elusive subatomic particles. They have a very small mass and do not have any electric charge. They interact with other matter so weakly that a neutrino produced in the core of the sun can fly through the entire Earth without hitting a single atom. Trillions of them are passing through your body every second, and you do not feel a thing. Because they interact so weakly, they decoupled from the rest of the matter, and radiation in the early universe much earlier than photons did. While photons were trapped in the plasma soup until 380,000 years after the Big Bang, neutrinos were set free when the universe was only about 1 second old. The Big Bang model predicts that these primordial neutrinos should still be all around us, forming a cosmic background similar to the cosmic microwave background. This is called the cosmic neutrino background CNB. However, because these neutrinos have been traveling for almost 13.8 billion years, they have lost almost all of their energy due to the expansion of the universe. They are now extremely cold and slow-moving, making them incredibly difficult to detect directly. Our current technology is not sensitive enough to pick them up. So, if we cannot detect them, how can they be evidence? The answer is that they have a subtle, indirect effect on the universe that we can measure. Even though they are ghostly, they still have mass and exert a tiny gravitational pull. Their presence in the early universe would have slightly altered the way structures grew, and would have left a faint imprint on both the cosmic microwave background and the large-scale distribution of galaxies. Cosmologists can build models of the universe with and without the CNB. They can then compare these models to our precise measurements of the CMB fluctuations and the patterns of galaxies from surveys. The results are clear. The models that include the cosmic neutrino background are a much better fit to the data. The subtle effects of these ancient neutrinos, predicted by the Big Bang model decades ago, are now being seen in our most sensitive cosmological data. For example, their presence slightly smooths out the growth of structure on small scales and leaves a specific signature in the CMB's polarization patterns. While a direct detection remains a holy grail for particle physicists, the indirect evidence for the CNB is very strong. It is another successful, non-trivial prediction of the Big Bang model. Number 10, the temperature of space is not zero. In the 19th century, the prevailing idea was that the universe was infinite, static, and eternal. If that were the case, space between the stars should be at absolute 0 to 173.15 degrees Celsius or 0 Kelvin. There was no known reason for empty space to have any heat. Even as late as the 1940s, physicists like George Gamow, who were working on the early hot universe ideas, were making predictions. Gamow and his colleagues Ralph Alpher and Robert Herman calculated that if the universe started in a hot, dense state and expanded, the leftover radiation from that initial fireball should have cooled to a temperature of about 5 Kelvin. This was a specific, testable prediction. However, at the time, the technology to detect such a faint, cold, all-sky signal did not exist, and the prediction was largely forgotten. Then came 1965 and the accidental discovery of the cosmic microwave background by Penzias and Wilson. They measured a background temperature of about 3.5 Kelvin. Later, more precise measurements, especially from the COBE satellite in the early 1990s, pegged the temperature at a very precise 2.725 Kelvin. The simple fact that intergalactic space is not at absolute zero, but is instead filled with a uniform bath of microwave radiation with a specific temperature is a monumental piece of evidence. A static, eternal universe has no explanation for this background glow. Where would the energy come from? Why would it be so perfectly uniform? Why a microwave spectrum? The Big Bang model explains it perfectly. The universe began in a state of near infinite temperature and density. As it expanded, it cooled. The radiation within it also cooled and had its wavelength stretched by the expansion. The light that was released at 380,000 years after the Big Bang, when the universe was at a temperature of about 3,000 Kelvin, like the surface of a red star, has been traveling through an expanding universe ever since. This expansion has stretched its wavelength by a factor of about 1,100. This stretching of the wavelength is what has cooled the radiation down to its current temperature of just 2.725 Kelvin. The discovery of the CMB was the event that moved the Big Bang from a fringe theory to the mainstream consensus. The fact that empty space has a temperature is a direct remnant of a time when the entire universe was as hot as a star. Number 9. The darkness of the night sky is a clue. Why is the sky dark at night? This might sound like a simple, almost childish question. The answer seems obvious because the sun is on the other side of the Earth, but for centuries this question, known as Olbers' paradox, was a profound cosmological puzzle. The paradox was formally stated by the German astronomer Heinrich Olbers in the 1820s. It goes like this. If the universe is infinite in size, infinitely old, and uniformly filled with stars, then no matter which direction you look, your line of sight should eventually end on the surface of a star. The entire sky should be as bright as the surface of the sun day and night. Think of standing in a dense, infinite forest. No matter which direction you look, you will see a tree trunk. You cannot see through the forest. In the same way, in an infinite, eternal universe full of stars, you should not be able to see any dark space between them. The entire celestial sphere should be a blazing wall of light. People tried to come up with solutions. Maybe, dust clouds between the, stars block the light, but that does not work. Over an infinite amount of time, the dust clouds would absorb so much energy from the starlight that they would heat up and glow just as brightly as the stars themselves. The Big Bang model resolves Olbers' paradox beautifully by challenging its two main assumptions. First, the universe is not infinitely old. It had a beginning, about 13.8 billion years ago. This means that we can only see the light from stars and galaxies that are close enough for their light to have reached us in that time. There is a horizon to our observable universe. The light from stars beyond this horizon has not had time to get here yet. Second, the universe is not static, it is expanding. As light from distant galaxies travels towards us, the expansion of space stretches the light's wavelength. This is redshift. The farther away a galaxy is, the more its light is redshifted. Or light from the most distant objects is redshifted so much that its energy is shifted out of the visible spectrum into the infrared and microwave range. This makes distant objects much dimmer and less energetic than they would be in a static universe. The combination of these two factors, a finite age and an expanding space, means that most of the light from distant stars never reaches us, or reaches us with so little energy that it does not contribute to the brightness of the night sky. The simple, profound darkness you see when you look up at night is a direct consequence of the universe having a beginning and expanding from that point. Number 8. The oldest stars are not infinitely old. One of the most basic predictions of the Big Bang model is that the universe has a finite age. By measuring the current rate of expansion and running the clock backward, we can calculate how long it has been expanding. Based on our best modern measurements, particularly from the Planck satellite's observations of the CMB, the age of the universe is 13.8 billion years. This is a very specific claim. A critical test of the model is to see if we can find anything in the universe that is older than this. If we were to find a star that was, say, 20 billion years old, the Big Bang model would be in serious trouble. Astronomers have spent decades developing methods to determine the ages of the oldest stars. One of the best ways to do this is by studying globular clusters. These are dense spherical collections of hundreds of thousands of stars, all born at roughly the same time. They are like cosmic retirement homes. By looking at the types of stars that are still burning in a globular cluster, we can determine its age. Massive stars burn through their fuel very quickly in just a few million years. Less massive stars, like our sun, burn for billions of years. The least massive stars burn for trillions of years. In an old globular cluster, all the massive, bright blue stars have long since died. The most massive star still shining tells us the age of the cluster. This is called the main sequence turnoff point. Using this method, and others involving the radioactive decay of elements like uranium and thorium in very old individual stars, astronomers have consistently found that the oldest stars in our galaxy are about 12 to 13.5 billion years old. The oldest known star, HD 140,283, nicknamed the Methuselah star, has an estimated age of about 14.27 billion years, but with an uncertainty of about 0.8 billion years. This means its age is consistent with being slightly younger than the universe itself. The key point is that we have never found a star that is definitively older than the 13.8 billion year age predicted by the Big Bang. The ages of the oldest objects we can find fit comfortably within the age of the universe. This provides a crucial consistency check for the entire cosmological model. It tells us that our understanding of the universe's timeline, from its first moments to the formation of the first stars, is coherent and self-consistent. The universe is old, but it is not infinitely old. Number 7, the cosmic web of galaxies matches a specific pattern. When we map the locations of galaxies in 3 dimensions, they are not spread out randomly like seeds scattered on a lawn. Instead, they form a vast, intricate structure, often called the cosmic web. Galaxies are clustered together in groups and massive clusters. These clusters are linked by long, thin filaments of galaxies stretching for hundreds of millions of light years. In between these filaments are enormous, almost empty regions called voids. The universe on this scale looks something like a sponge or a network of neurons. The existence of this structure itself needs an explanation. Why did matter clump in this specific way? The Big Bang model, combined with the theory of inflation and the existence of dark matter, provides a detailed answer. In the very early universe, there were tiny quantum fluctuations in density. Inflation stretched these microscopic fluctuations to astronomical scales. These slightly denser regions were the seeds of all future structure. The model also includes two main types of matter: normal matter, baryonic matter, which makes up stars and planets, and dark matter, a mysterious substance that only interacts through gravity. Or dark matter makes up about 85% of the matter in the universe, because dark matter does not interact with light. It could start clumping together under gravity long before normal matter could. It formed a gravitational scaffolding. After the universe became transparent at 380,000 years, normal matter was then able to fall into these pre-existing wells of dark matter. Computer simulations are a powerful tool to test this model. Cosmologists can start a simulation with the initial conditions measured from the cosmic microwave background assistant, a nearly uniform distribution of dark matter and normal matter with tiny density fluctuations, and let it evolve over 13.8 billion years according to the laws of physics. The results are stunning. These simulations naturally produce a cosmic web that looks remarkably like the one we observe through our galaxy surveys. They correctly predict the sizes of the voids, the thickness of the filaments, and the masses of the galaxy clusters. They show how the universe evolves from a smooth, simple state into the complex, structured cosmos we see today. The remarkable agreement between the observed large-scale structure and the predictions of these simulations is one of the most compelling pieces of evidence for the entire Big Bang paradigm, including the crucial roles of inflation and dark matter. Number 6, gravitational waves from the beginning have been found. On September 14th, 2015, two detectors, one in Livingston, Louisiana, and one in Hanford, Washington, simultaneously felt a tiny tremor. It was not an earthquake, it was a ripple in the fabric of space-time itself. This was the first direct detection of gravitational waves, a phenomenon predicted by Albert Einstein exactly 100 years earlier. The signal, named GW15914, was generated by the cataclysmic merger of two black holes, each about 30 times the mass of the Sun, more than a billion light-years away. This discovery, made by the Laser Interferometer Gravitational Wave Observatory LIGO, opened a completely new window on the universe. While the gravitational waves detected by LIGO are from relatively recent astrophysical events, the Big Bang model predicts that gravitational waves should also have been created in the universe's most extreme moments. The period of cosmic inflation, in the first fraction of a second, would have been an incredibly violent process, shaking space-time itself and generating a background of primordial gravitational waves. These waves would still be propagating through the universe today, but they would be far too faint for an instrument like LIGO to detect. However, they should have left an imprint on the cosmic microwave background. Specifically, they would create a unique swirling pattern in the polarization of the CMB light, the B modes mentioned earlier. The search for these primordial B modes is one of the most active fields in cosmology. A confirmed detection would be smoking gun evidence for inflation, but there is another way that gravitational waves provide evidence. The Big Bang model, combined with general relativity, predicts the abundance of light elements created in the first few minutes Big Bang nucleosynthesis. The rate of the universe's expansion during that time is a critical factor in these calculations. If there were other types of light, relativistic particles present besides photons and the known neutrinos, it would have made the universe expand faster, changing the predicted amounts of helium and deuterium. Gravitational waves can constrain the number of these relativistic species. By comparing the element abundances with the expansion rate measured from gravitational wave events like merging neutron stars, which also produce light, we can test this key part of the early universe model. So far, the results are perfectly consistent with the Standard Model's prediction of 3 types of neutrinos and no other exotic particles. Gravitational wave astronomy is a young field, but it has already provided a new independent way to verify the conditions of the early, hot, dense universe as described by the Big Bang. Number 5. The tiny fluctuations in the oldest light. For many years, a major challenge for the Big Bang model was explaining where galaxies came from. The cosmic microwave background CMB appeared to be perfectly smooth. If the early universe was perfectly uniform, how did it ever clump together to form the stars and galaxies we see today? There would be no reason for gravity to pull matter into one area more than another. The model needed some initial seeds or density variations. The theory of inflation predicted that there should be tiny quantum fluctuations in the early universe that were stretched to macroscopic sizes, and these should be visible as tiny temperature variations in the CMB. In 1992, the NASA Cosmic Background Explorer COBE satellite made a landmark discovery. After carefully mapping the entire sky, it found what it was looking for: tiny fluctuations in the temperature of the CMB. These variations were minuscule, just 1 part in 100,000. But they were there. This was the discovery of the seeds of cosmic structure. The slightly hotter spots were slightly less dense regions, and the slightly cooler spots were slightly denser regions. These denser regions had more gravity and would eventually grow into the galaxy clusters and superclusters we see today. The COBE discovery was so important for confirming the Big Bang model that its lead scientists, George Smoot and John Mather, were awarded the Nobel Prize in Physics in 2006. In the decades since COBE, 2 more space missions, the Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite, have mapped these temperature fluctuations with much higher precision. These detailed maps are a cosmological goldmine. The specific pattern of the hot and cold spots, their sizes, how they are distributed, and their relative strengths contains a huge amount of information about the early universe. By analyzing this pattern, cosmologists can determine key parameters of the universe with incredible accuracy. These include the age of the universe, the amount of normal matter, the amount of dark matter, the amount of dark energy, and the geometry of space. The values we get from the CMB are perfectly consistent with the values we get from other completely independent methods like observing supernovae or mapping the distribution of galaxies. This powerful consistency across different types of observations is what gives scientists such high confidence in the Big Bang model. The tiny ripples in the CMB are not just evidence, they are the blueprint for the entire cosmos. Number 4, the abundance of helium and other light elements. About 3/4 of the normal matter in the universe is hydrogen. Almost all of the remaining quarter is helium. There are only trace amounts of everything else. Why this specific ratio? Stars fuse hydrogen into helium in their cores. But the universe is not old enough, and there are not enough stars to have produced all the helium we see. Most of it must have been created somewhere else. The Big Bang model provides a precise explanation for where it came from. This process is called Big Bang nucleosynthesis, BBN. In the first few minutes after the Big Bang, the universe was incredibly hot and dense, like the core of a massive star, but much hotter. It was a sea of protons, neutrons, electrons, and photons. As the universe expanded and cooled, protons and neutrons could begin to fuse together. The theory of BBN makes very specific, testable predictions about how much of each light element should have been created. The process was a race against time. The universe was cooling and becoming less dense very quickly. This meant there was only a short window, from about 1 minute to 3 minutes after the Big Bang, when the temperature and density were just right for fusion to occur. The calculations depend on only one key parameter: the density of normal baryonic matter in the universe. Once you have that number, the physics predicts the primordial abundances of several light isotopes: hydrogen, deuterium, an isotope of hydrogen with 1 proton and 1 neutron, helium-3, helium-4, and lithium-7. For decades, astronomers have been measuring the amounts of these elements in the most pristine, ancient environments they can find, like very old stars or distant gas clouds that have not been significantly contaminated by stellar processes. The results are a stunning success for the Big Bang model. The measured abundances of hydrogen, deuterium, and helium match the predictions of BBN, using the baryon density measured from the CMB, with remarkable precision. The model predicts that about 24% of the ordinary matter should be helium-4. Observations confirm this. It correctly predicts the tiny amount of deuterium, an isotope that is easily destroyed in stars, so any we see must be primordial. The prediction for lithium is a bit off, which is an ongoing puzzle, but the incredible success with the other elements is considered one of the three great pillars of Big Bang evidence, alongside the expansion of the universe and the CMB. Number 3. Galaxies are flying away from us. In the 1920s, the universe was thought to be a static place. It was generally believed that the Milky Way galaxy was the entire universe. Other fuzzy patches in the sky, called spiral nebulae, were thought to be gas clouds or forming star systems within our own galaxy. An astronomer named Vesto Slipher had been studying these nebulae. He used a technique called spectroscopy, which splits the light from an object into its constituent colors like a prism. He noticed something strange. The light from almost all of these nebulae was shifted towards the red end of the spectrum. This is called redshift. Redshift is a result of the Doppler effect. Just as the pitch of a siren sounds lower as it moves away from you, the wavelength of light from an object moving away from you gets stretched out, making it appear redder. Slipher had found that almost all of these nebulae were moving away from us, and some at very high speeds. Then, in 1929, an astronomer named Edwin Hubble made a discovery that would change our understanding of the cosmos forever. He had been using the new 100-inch Hooker telescope at Mount Wilson Observatory in California to measure the distances to these spiral nebulae. He managed to do this by observing a specific type of pulsating star called a Cepheid variable within them. By measuring their distances, he first proved that these nebulae were not inside our galaxy. They were entire island universes or galaxies in their own right, millions of light years away. But then he did something else. He combined his distance measurements with Slipher's redshift measurements. He found a clear and startling relationship. The farther away a galaxy was, the faster it was moving away from us. This relationship is now known as Hubble's law. It is the cornerstone of modern cosmology. This was the first direct observational evidence that the universe is not static. It is expanding. It is important to understand what this expansion means. The galaxies are not flying through space away from a central point. Instead, space itself is stretching, carrying the galaxies along with it. A good analogy is to imagine baking a raisin loaf. As the dough rises, every raisin moves away from every other raisin. A raisin does not have a center of expansion. From the perspective of any single raisin, all the others appear to be moving away from it. This is exactly what we see in the universe. No matter which galaxy you are in, all other galaxies outside of our local gravitationally bound group would appear to be moving away from you. The discovery of this universal expansion is the observation that led directly to the idea of the Big Bang. If everything is moving apart now, it must have been closer together in the past. If you run the clock backwards far enough, everything must have been in the same place at the same time in an incredibly hot, dense state. Number 2, the cosmic microwave background is too perfect. When Penzias and Wilson first discovered the cosmic microwave background CMB in 1965, they found a faint, uniform glow of microwaves coming from every direction. The Big Bang Theory predicted this afterglow, but it also made a much more specific prediction about the nature of this light. It predicted that the spectrum of this radiation, the intensity of the light at different frequencies, should have a very specific shape. It should be a blackbody spectrum. A blackbody is a theoretical perfect absorber and emitter of radiations. The light it gives off has a characteristic bell-shaped curve that depends only on its temperature. For example, a hot piece of iron glows red, then orange, then white as it gets hotter. The spectrum of the light it emits is a blackbody spectrum for that temperature. The Big Bang Theory predicted that the CMB must have a perfect blackbody spectrum because in the early universe, the cosmos was in a state of perfect thermal equilibrium. The dense plasma of particles and photons was opaque, meaning the light and matter interacted so frequently that they all shared the same temperature, just like the atoms inside a hot oven. When the universe became transparent, the light released at that moment should have preserved this perfect thermal fingerprint. For decades after the CMB's discovery, astronomers tried to measure its spectrum from the ground and with balloons, but the Earth's atmosphere absorbs microwaves, making a precise measurement impossible. It was a crucial test of the theory that remained unconfirmed. The definitive answer came in 1990 from NASA's Cosmic Background Explorer COBE satellite. On board was an instrument called the Far Infrared Absolute Spectrophotometer FIRAS, designed specifically to measure the CMB spectrum. When the data came back and were first presented at a meeting of the American Astronomical Society, the room was stunned into silence, followed by a massive standing ovation. The data points on the graph of intensity versus frequency were not just close to the theoretical blackbody curve, they landed perfectly on it. The error bars on the data points were so small they were not even visible on the plot. It was, and still is, the most perfect blackbody spectrum ever measured in nature. This result was a spectacular confirmation of the Big Bang model. Any other proposed source for this background radiation, like starlight scattered by dust, would not produce such a perfect blackbody spectrum. The CMB's perfect thermal nature is a direct photograph of the hot, dense equilibrium state of the early universe. Number 1, the entire universe is expanding. The single most fundamental piece of evidence for the Big Bang is the expansion of the universe. This is not a theory. It is an observed fact, confirmed by countless measurements over nearly a century. Every piece of evidence we have discussed, from the CMB to the abundance of light elements, is built upon this foundational observation. Without an expanding universe, none of the other evidence makes sense. The expansion is what stretches the light from the Big Bang into the microwaves we see today. The expansion is what cooled the universe from a hot plasma to the cold vacuum of today. And the expansion rate in the first few minutes determined how many light elements were forged. The expansion is what resolves the paradox of the dark night sky. Edwin Hubble's 1929 discovery that distant galaxies are moving away from us with a speed proportional to their distance was the first proof. We measure this through redshift. When we look at the light from a distant galaxy, we see specific spectral lines, which are like fingerprints of the elements in that galaxy's stars. We know what wavelengths these lines should be from experiments in labs on Earth. In distant galaxies, these lines are all shifted to longer, redder wavelengths. This redshift, denoted by the letter Z, is a direct measure of how much the universe has expanded since the light left that galaxy. The galaxy that holds the current record for the most distant known has a redshift of Z equals 13.2, meaning the universe has expanded by a factor of 14.2 since that light began its journey. We have mapped this expansion with incredible precision using various methods. We use Type Ia supernovae, which are a type of exploding star that always has the same intrinsic brightness. By comparing how bright they appear to how bright they should be, we can calculate their distance. By measuring their redshift, we can measure their speed. This data, which led to the 2011 Nobel Prize in Physics, not only confirmed the expansion, but showed that it is accelerating, driven by a mysterious force called dark energy. We can also measure the expansion using the baryon acoustic oscillations BAO, the fossilized sound waves in the distribution of galaxies. The BAO gives us a standard ruler of a known size, and by measuring how large that ruler appears at different distances, we can map the expansion history of the universe. All of these different independent methods give a consistent picture of a universe that has been expanding for 13.8 billion years. This expansion is the direct, ongoing, observable consequence of the initial event we call the Big Bang. It is happening right now, all around us. The space in the room you are in is expanding, though the effect is so small on this scale that it is completely overwhelmed by local forces. But on a cosmic scale, the expansion is the dominant force that has shaped the universe from a singular point in the distant past into the vast, complex cosmos we inhabit today.